Have you ever wondered how multiple users can access and manipulate the same database at the same time without causing data inconsistencies? This is a question that has puzzled many, and the answer lies in the realm of multi-user database management system, or DBMS architectures. These architectures are like the invisible conductors of a symphony, orchestrating the concurrent access to a database by multiple users or applications, while ensuring that the music of data consistency, integrity, and isolation remains harmonious. The complexities of managing shared access to data in a multi-user environment have led to the development of several unique and fascinating architectures. Each architecture has its own strengths and weaknesses, and understanding them can help us make better decisions when designing and implementing database systems. So buckle up as we delve into the intricate world of DBMS architectures. In our journey today, we will explore different types of multi-user DBMS architectures. Let's dive into our first architecture, the client-server architecture. A fundamental design in the world of database management systems, this architecture is split into two main components, the client and the server. Imagine a restaurant scenario. The client or the diner places an order or a request. The server or the waiter takes this order and delivers it to the kitchen or the database. The kitchen then processes the order or the request, and the server brings the meal, or the results, back to the client. This is a simplified analogy of how the client-server architecture works. The client, typically a user or an application, interacts with the server by sending requests for data. The server, on the other hand, is responsible for managing the database. It processes the client's requests, executes queries, and returns the results back to the client. This architecture can be further divided into two subtypes, 2-tier and 3-tier. In a 2-tier architecture, the client communicates directly with the server, just like a diner speaking directly to a waiter. It's a straightforward, efficient process, but it can sometimes put a lot of load on the server, especially if there are many clients making requests at the same time. In a 3-tier architecture, there's an intermediary, like a head waiter. The client sends requests to an application server, which then interacts with the database server. This middle layer can manage business logic, user interface, and data access, distributing the load more evenly and providing an extra layer of abstraction and control. However, both these subtypes share the same core principle. The client makes a request, and the server processes it and returns the results. It's a dance of requests and responses, creating a dynamic interplay between the two components. So that's the client-server architecture, a fundamental design in DBMS. It's like a well-choreographed dance, with the client and server moving in harmony to ensure smooth data management and retrieval. Next in line is the shared nothing architecture. This unique architecture is designed to be truly independent. Every node or server in a distributed system has its own separate resources, including the central processing unit, memory, and storage. Imagine a cluster of islands, each with its own resources and self-sufficient operations. This is what shared nothing architecture is like. Each island or node communicates with others through a network, but they don't share any resources. It's all about self-sufficiency. This architecture often utilizes data partitioning techniques to distribute data across multiple nodes, reducing contention and improving scalability. Let's think about a large warehouse with several independent sections. Each section operates independently, but communicates with others for overall efficiency. That's a practical example of how shared nothing architecture works. This architecture is commonly found in distributed databases and parallel processing systems. Its independence and self-sufficiency make it a scalable and efficient choice for many applications. That's the shared nothing architecture, known for its scalability. Now, let's look at two distinct architectures, the shared disk and the peer-to-peer architectures. First up, the shared disk architecture. This is a setup where multiple nodes or servers share access to a common storage or disk subsystem. Imagine a group of friends sharing a single wardrobe. Each friend has their own outfits, but they all use the same wardrobe to store and retrieve their clothing. In the same way, each node in a shared disk architecture has its own processing power and memory, but all nodes access the same shared storage to retrieve or modify data. Now you might be thinking, what happens if two nodes try to access the same data at the same time? Well, that's where coordination mechanisms come into play. Things like locking or distributed concurrency control protocols are used to ensure data consistency and integrity. This way, no two nodes are stepping on each other's toes, so to speak. Shared disk architectures are commonly used in clustered database systems and some high-availability configurations. Next, we have the peer-to-peer or P2P architecture. This one is a bit different. In a P2P setup, all nodes in the network have equivalent capabilities and responsibilities. They can act as both clients and servers. If we go back to our friend's analogy, it's like every friend having their own wardrobe and being able to borrow clothes from each other's wardrobes directly. Each node can directly communicate and exchange data with other nodes without needing a central server. This makes P2P architectures decentralized, highly scalable, and fault-tolerant. However, they can face challenges in maintaining consistency and coordination, especially in large-scale networks. So there we have it, the shared disk architecture with its communal storage system and the peer-to-peer architecture with its decentralized structure, each with its own unique advantages and challenges. These are just two of the many ways we can structure systems to handle the complexities of managing shared access to data in a multi-user environment. Shared disk and peer-to-peer, two architectures offering unique advantages. Our final stops are the centralized and hybrid architectures. Let's begin with centralized architecture. Picture a single central server doing all the heavy lifting. It's responsible for all data processing and management tasks. Clients or users, they interact directly with this central server to access and manipulate data. The beauty of it lies in its simplicity. Implementing and managing a centralized architecture is straightforward. You've got one server, one point of control, but every rose has its thorns, and so does the centralized architecture. Scalability and performance can become serious roadblocks, especially in large-scale or distributed environments. Imagine a bustling city with only one supermarket. Sounds chaotic, right? That's what happens when a single server gets overwhelmed with increasing data and user requests. So, how do we navigate these limitations? Enter hybrid architectures. Think of them as the best of all worlds. They combine elements of different architectures, cherry-picking the strengths and sidestepping the weaknesses. For instance, a system might employ a client-server architecture for front-end interactions with users. It's like having friendly, efficient cashiers at the supermarket to handle customer transactions. Then it might use a shared nothing architecture for data processing and storage. This is like having multiple storage rooms, each with its own stock, reducing the pressure on any single one. By using a hybrid approach, systems can achieve optimal performance and scalability. They can provide a smooth, efficient service to users, like a well-run supermarket in our city analogy. However, keep in mind, managing such a system can be complex. You're not dealing with one type of architecture, but a blend. So, you need to have a clear understanding of the individual components to make the most of a hybrid architecture. There you have it. Centralized and hybrid architectures, each with its own strengths and weaknesses. The choice between them depends on the specific needs and constraints of your system. So choose wisely and remember, the right architecture can make all the difference. So we've covered quite a bit about DBMS architectures today. We began with the client-server architecture, where the DBMS is divided into two main components, the client and the server. This structure can be organized into two-tier or three-tier architectures, with the client interacting either directly with the server or with an intermediary application server. We then moved on to the shared nothing architecture. In this setup, each node has its own independent resources, and there's no sharing of resources across nodes. This architecture is a common choice for distributed databases and parallel processing systems, as it reduces contention and improves scalability. Next, we delved into the shared disk and peer-to-peer architectures. In shared disk architecture, multiple nodes share a common storage or disk subsystem, and coordination mechanisms ensure data consistency and integrity. Peer-to-peer architecture, on the other hand, is decentralized, with all nodes having equivalent capabilities. Each node can directly exchange data with others, providing scalability and fault tolerance, although maintaining consistency can be challenging. We also discussed the centralized architecture, where all data processing and management tasks are performed by a single central server. While this architecture is simple to implement and manage, it may face limitations in scalability and performance in large-scale or distributed environments. Finally, we examined hybrid architectures, which combine elements of different architectures to leverage their strengths and mitigate their weaknesses. For example, a system might use a client-server model for front-end user interaction, while opting for a shared nothing structure for distributed data processing and storage. Throughout this journey, we've highlighted how each architecture has its unique strengths and potential limitations. The key takeaway is that the choice of architecture should align with your specific needs and constraints. Whether you're dealing with a small centralized database or a large-scale distributed system, the right architecture can make all the difference in ensuring efficiency, scalability, and data integrity. Remember, there's no one-size-fits-all solution in DBMS architectures. It's all about finding the right fit for your specific needs.